Hey guys, welcome to this video on calculating the magnitude of the electric field. This is a follow-up to the introduction to the electric field video, so if you haven't checked that one out, you want to check it out, otherwise this one will be quite confusing. Additionally, remember that I always recommend watching the videos at a slightly higher playback speed because I record them a little bit slower so that I can make things clearer. Alright, jumping right into it, we have over here a sphere. Well, it's represented as a circle, and it's a charged value that is positively charged, and so Q, remember, stands for charge, and we have showing that it's positive. And what this charge is going to do is create an electric field in the space around it. And I want to be able to calculate what the magnitude of the electric field would be at a particular location somewhere around it. So, as we described in the introduction video, the electric field, uppercase E, can be calculated in one of two ways. It's describing the amount of electrostatic force that's exerted or that would be exerted per unit of test charge placed at a particular location. If we substituted in Coulomb's law equation into this, we would get that we have kq divided by r squared once the other q, the test charge q, is simplified out of the equation. So just some reminders of some of the lingo here. The thing that's creating the electric field is known as the source charge. So the source charge is the origination of the electric field. And this uppercase Q here, although you can also make it a lowercase q, it doesn't really matter. The main thing to note is that in this equation, the Q that is here represents the source charge. It's the thing that's making the electric field, not the thing that is being placed in the field. The thing that we're going to place at a particular location, so say we wanted to put another little charged particle right over there, that thing is known as the test charge, and that's what this Q represents. Now again, you can interchange lowercase and uppercase, it doesn't really matter, but you just have to remember that in the equation, the Q that's being used here to describe the electric field is different. So this is a test charge, or something that I would place at that location. Now the reason that it's called a test charge is that if you place something here, you can test what the electric field strength is, or what direction the electric field is oriented. And so that's where this term comes from. Now one thing that you might see a lot in problems and textbooks is also this term point charge. And actually this term is more generic, and you can really use it interchangeably with either of these. However, most sources that I've seen are going to refer to point and source charges maybe as the same thing, and test charges as something else. Where this term point comes from is kind of like when you think about masses in classical mechanics. We usually are dealing with a mass for the most part as just a point mass, meaning we're only looking at its center of mass. So you don't really have to worry about what the shape of the object is, you just have to worry about the point that it's located at, if you will. So anyway, thinking about those things is very important. Now when we're calculating the magnitude of the electric field, what we're trying to know is how strong the electric field is, and not necessarily what direction it is oriented. Because what we're going to see is that the electric field can either attract or repel different things, right? So if I have a positive source charge here, if I place another little positive charge at this location right here, I know that it's going to be repelled and be pushed or accelerated out in this direction. Whereas if I place a little negative test charge over here, it would be attracted. So we can see that the electric field can have a different direction depending on what kind of source charge you have located. Now that's very different for the gravitational force, because the gravitational force is going to be considered only attractive and it can't repel. So the direction of the gravitational field is usually a lot easier to determine than for the electric field. But we have some conventions that we will discuss in subsequent videos. So let's take a look at, if I wanted to actually calculate the magnetic field, the magnitude of the electric field at this location, let's say right here. Now I'm going to say that this is maybe, let's make it 0.01 meters away from this source charge. and I want to know what the value of the electric field is. Well, I can use the equation E equals KQ over R squared, and assigning my variables values here, I know that Coulomb's constant is approximately 9 times 10 to the 9th in the units of Newton meters squared per Coulomb squared. And then we have our R value here of 0.01. And then we need a Q value for the source charge in order to determine the electric field. Now let's say that this Q value is, I'll just make up a random number here. Let's say it's 5 microcoulombs, because 1 coulomb is actually very big, and so we usually will see things more in micro and nanocoulombs. This converts to 5 times 10 to the negative 6 coulombs with the micro prefix. Now it's very easy, and I'm not going to go into the details of just plugging in the numbers. Just make sure you always square your R value, and what will spit out is the electric field value. What I more so want to focus on is the idea of the fact that we're only looking at the magnitude of the electric field here. We need to make sure that we always put an absolute value around the Q. Now the reason for that is the most important thing moving forward, because I know that all of you can already plug and chug values. That's not so difficult. So why do we actually have to put this in here, and how is this going to affect answers in the future? Well, it's more than just dropping a negative sign or adding a positive sign. You want to think of it in the following way. Q values can have two different signs. So when we talk about a sign on the Q value, we're saying, is it the type of charge that's considered positive charge, or is it the type of charge that's considered a negative charge? So this is what is actually describing the type of charge. Now that is not a a vector quantity. That doesn't have anything to do with direction. It's just telling us that the kind of charge is positive or the kind of charge is negative. And that's why we need to put the absolute value here. The reason we want to put the absolute value is so we do not contaminate the answer or the sign of the answer, because the electric field, being a vector quantity, can also have a sign assigned to it. And the sign could be positive or negative. And you have to be careful, because this positive or negative for the electric field does not mean the same thing as this positive or negative for the type of charge. This positive or negative is actually going to tell you the direction of the field at that particular location R that you plug in. Now, what's really important here is that you remember that we use vector signs here to help us indicate if the electric field is oriented, say, in the positive direction to the right or up, or the negative direction down to the left, or maybe we want to switch those and make negative direction up. So it's really arbitrary, but it's not the same thing as this, and so it's extremely important to put the type of charge sign in an absolute value so it does not contaminate the answer of the electric field. So calculating the magnitude of the electric field would just be getting a numerical value for this E and not being concerned with whether you have a positive or negative sign. In the next video, we're going to take a look at how you actually determine the direction of the electric field, because it's not going to be the same in every location.